Watch an AI generate a robot picking up a cup. The video looks perfect, photorealistic, gorgeous, and then you look closer. The gripper passes straight through the table. The cup it supposedly pushed never moved. The object it grabbed drifts off into thin air. It is a beautiful lie. And if a robot tries to learn from that lie, it inherits every single mistake. A new paper called Physisforcing just taught video models to finally obey the physics, but only where it actually matters. And the trick is genuinely clever. Here is why this is hard. General video models, Sora, Wan, they make stunning frames, but they have never seen real robot contact, so they hallucinate the interactions. Robot-specific fine-tuning helps, but it treats every pixel the same. The background wall gets the exact same supervision as the gripper touching the cup. Geometry methods track points but miss meaning. They see motion without knowing a pushed object should move away. And preference methods, DPO, GRPO, they correct after the fact sparingly. Nobody aligned the physics directly where it breaks. Physisforcing's insight is almost obvious once you hear it. Physics violations in robot videos are not everywhere. They are hierarchical and region localized. They concentrate at the gripper, at the contact point, at the moving object. The rest of the frame, the table, the wall, the background, that is almost always fine. So do not supervise physics everywhere. Find the physics informative regions and align lie those. It is like a driving instructor who only corrects you at intersections instead of nagging the whole highway. Targeted correction, zero wasted effort. First step, find those regions automatically. They run CodeTracker 3, tracking 625 points across the video. Points that move a lot get a high motion score. Then depth anything. V2 estimates depth and flags the foreground. Multiply motion by foreground and you get a physics score for every point. Keep the points above average, mask out the rest. What survives is a clean spatiotemporal mask over the gripper, the contacts, the moving objects, the pixels where physics actually lives. Then two alignment losses, both applied only under that mask. Loss 1, pixel level. The model has to predict where tracked points should move, using its own internal features, so trajectories stay continuous instead of teleporting. That kills the gripper jump failure. Loss 2, semantic level. They borrow a frozen V, JEPA2 encoder, the one that understands object coupling and contact, and force the video model's token relationships to match it inside the masked regions. Pixel continuity from below, semantic coupling from above, both training only. Zero extra cost at inference. The numbers. On our bench, the physics benchmark, their PF Cosmos model scores 63.8. That beats the commercial giants, Wan 2.6 at 60.7, and even Sora on the embodiment dimensions. But the real proof is this, compared to the base model, plus 11.3. And compared to vanilla robot fine-tuning, plus 4.1. The physics losses stack on top of normal training. You're not trading visual quality for physics, you get both, and it transfers to real control. When they plug the physics-aware video model into a closed-loop action planner, success rate jumps from 16% to 24%. A full 8-point absolute gain, beating every other world model planner they tested. A robot policy trained on these videos inherits fewer lies, so it fumbles less in the real world. Better simulator, better robot. Why does this matter? Because embodied AI is starving for training data, and generated video is supposed to be the cheap synthetic flywheel. But a flywheel of physically wrong videos teaches robots the wrong lessons. Physisforcing makes generated worlds trustworthy enough to learn from, and it does it cheaply, region-focused, no inference tax. Pretty frames were never enough. Pretty plus physical was the unlock. So the takeaway. 1. Robot video models look great but lie about physics exactly where it matters most, at the contact. 2. Physisforcing aligns only those physics, informative regions with 2 training-only losses. 3. It beats both base models and vanilla fine-tuning, and lifts real robot success. Beautiful was never enough. The physics had to come along. Paper and project page below. Subscribe, because the next simulator is even stranger.